In this lesson, we're talking about percent error in graphing. And we've been discussing how basically measurements will vary in their precision, but no matter how precise something is, a measurement is, it probably is not accurate because there's always a little bit of error that's involved in any measurement, no matter what device you use. Accuracy refers to how close a value is to its accepted value. And the percentage error, or the percentage difference, is the absolute value of the difference between the experimental and accepted values, expressed as a percentage of the expected value. Here's a formula that we'll often use during labs. When a student may want to express how close their value that they obtained was to something that is accepted in general as being the true value. The absolute value bars, what they do is that they just clear out any negatives. So really, it doesn't matter whether your value, your experimental value that you obtained, is higher than the accepted value or lower than the accepted value. It just matters how far apart they are. And you're going to use this calculation often to determine the accuracy or validity of results in your lab experiments. Here's an example, and this is an example that's pulled from a grade 12 course where one of their first labs is to calculate the speed of light. And so the expected value of the speed of light, or the accepted value, is 2.998 times 10 to the 8th meters per second. And so what we should have there is we should have, there should be a unit, meters per second, excuse me. But oftentimes you'll see this as 3 times 10 to the 8th, but it's actually 2.998. So various groups in a physics class obtained the following values in a lab experiment. Find their percent error. And these were two values that I took straight from results from the grade 12s. So one group got 2.4 times 10 to the 8th. How close were they? Well, let's take a look at our percent error calculation. And here, what we'll do is we'll take the experimental result and we'll subtract it from the accepted result. And you'll notice that the experimental result is smaller than the accepted. It doesn't matter. We get a negative in our numerator, but the absolute value signs take care of that, and we don't have to worry about it. So when we divide by the accepted value again, we get 19.95. And of course, when we multiply by 100, that rounds to 20%. So that's what we'd end up with. If you don't multiply by 100, then you just get a decimal value. And we know that the decimal value does the exact same thing. It just expresses a percentage, but in general, you're going to express this as a percent. Here, this group got 7.3 times 10 to the 7th meters per second as their experimental value. So when we do the expected, or the percent error here, we get something much larger. So this group actually obtained a percent error of 75%. Very often in physics, we're going to be using graphing techniques. And so it's very easy to observe relationships between data by creating graphs rather than looking at tables of value. So it's very important to be able to produce graphs quickly and easily and to be able to extract information from them. So let's look back to our grade 9 and grade 10 math classes. Slope in general is equal to rise over run. And if we want to express that mathematically, we call slope m, and m is equal to the change in the y-coordinates over the change in the x-coordinates. So here's an example where we're going to calculate a couple of different slopes. In the first one, the points are given, and in the second one, we're going to calculate the points from the graph. We're going to read the points off the graph. So here's the first one. We've got point -1 and 2, and we've got point Q, which is 2 at -4. So here, slope is equal to y2 minus y1 over x2 minus x1. And we're going to call Q point 2, and we're going to call P point 1. It doesn't matter if you want to go the reverse and call P point 1 and Q point 2, you're going to get the same answer, and we end up with a slope of -2. Now, if we want to determine the equation of this line, no problem. The y-intercept, as we can see, is a 0. And so the equation of this line becomes y equals -2x. In example B, we need to read the points off of the line. And so I would leave this for an exercise for my students to do. But in general, hey, let's pick the intercepts. We can use them just as easily as anything else. But in the example, what we've actually used is we've used the point 6 and 3 and -6 and -1 as our points because they happen to pass right through lines. In general, we want to get as much spread as we possibly can. And so we end up getting a slope of 1/3 for this graph. The y-intercept of this, if we can take a look and we can see it's +1. So for a y-intercept of +1, we get our equation y equals 1/3 x plus 1. We need to be able to do this. This is, of course, a review of what you've done in your math classes, but it's important to remember. When it comes to graphing, some very, very important things to remember. Number one, the independent variable. That's the one that's controlled by the experimenter. That goes on the x-axis. It's a convention, we all do it, and that's the way it's got to be. The dependent variable, that's the one that is measured by the experimenter. It always goes on the y-axis. It's important that if you're doing this by hand, you use a pencil. Do not use a pen to create your graphs. It's important that you use a ruler. What's even more important than using a pencil and a ruler, I tell my students, is, hey, figure out how to use Microsoft Excel or another graphing program, another spreadsheet program like Numbers or something else that you have on your computer. Those programs can actually calculate the slope and the equation of the line really, really easily for you. And so that's something that you may want to look into. Label your axes, and don't just label them, but also include units in your labeling. It's really, really important. And along with labeling your axes, give the graph a descriptive title. Y versus X is not a descriptive title. Call it something that has meaning for what you're doing and what you're showing in the graph. Remember that the line of best fit, the LOBF, the line of best fit, must go through as many points as possible. So when we're trying to line up a line of best fit, it's got to go through as many points as possible. And the second thing is there should be an equal distribution of points both above and below the line.